Welcome to the another video on VLSI design. In this video, we are going to discuss a couple of exercise problems related to the CMOS structures. Before that, I would like to inform all the students, if you have any queries related to the VLSI design course, students are free to write in the comment section. And also, I would like to encourage the students to subscribe to this particular channel so that any update in the video you will be notified. So with that, let's move on to the exercise problems of chapter 1 from the textbook Weste. Okay, CMOS VLSI Design. That's going to be the title of the book. So let us take this problem, exercise problem 1.5. In this problem, it was asked to us for writing the CMOS structure for 4-input NOR gate. Okay, so let us follow the same approach what we have discussed in the very beginning and try to develop CMOS structure for the 4-input NOR gate. This is the Boolean expression for the 4-input NOR gate. Y equals A plus B plus C plus D whole bar. So this is a Boolean expression for the 4-input NOR gate. So let us now divide this into the two steps. First, let us develop the pull-up network followed by the pull-down network. Once these two network structures have been developed, then we can combine together these two networks that forms the CMOS structure. So first, let us focus on the pull-up network design. So again, rewriting the same expression for the 4-input NOR gate, y is equal to A plus B plus C plus D. So here we can apply De Morgan's theorem for the right hand side. And what does De Morgan theorem says that for two variable, De Morgan theorem says that A plus B whole bar equals A bar into B bar. The sum of complement is equal to complement of the product. Okay, that is the De Morgan's theorem. Now let us apply this De Morgan theorem for 4 variables here. So A plus B plus C plus D whole bar now becomes, after applying De Morgan's theorem, it becomes y equal to A bar dot B bar dot C bar dot D bar. So this is the simplified expression. Now here, with the help of this, we can write the CMOS structure. As we can see that whether the Boolean expression has met the required criteria or not. So here each variable is in complement form. That's again, it's very good. And the left hand side, the output variable is in the normal form. And here there are dots here that shows the transistors are connected in series. Totally 4 transistors. Each variable is taken as one transistor. So in this expression, there is a 4 variable A, B, C, D, and each variable is in the complement form, and that is required for the pull-up network. And there's a dot, for each, the entire. There are 3 dots here, so that shows that all these transistors are connected in series. So A, B, C, D are the 4 transistors that are connected in series. As we can see here, this is the transistor pull-up structure. So we take here for a pull-up structure is made up of only PMOS transistors. All PMOS transistors, 4 PMOS transistors are connected in series with input as A. Though the variable is in a complement form, but while writing the CMOS structure, so we should write a normal variable. So A is one input, so that is the forms, that is the input for this gate input for the upper PMOS transistor. Like this, we can connect 4 transistors in series. And you can see that for one of the transistor, which is a top transistor, we can connect with the power supply, which is VDD, and the other end of the series connection that is tied to the output Y. So this is the pull-up network. Similarly, we can also write the pull-down network. Again, rewriting the same 4-input NOR gate expression, Y equals A plus B plus C plus D whole bar. Now we can complement on both sides because we are bringing this expression which is suitable for the pull-down network. So therefore, let us complement both the sides of these expressions. So y becomes y bar, and a plus b plus c plus d, that becomes double complement. So double complement is nothing but it is, you can retain just an expression, because a bar whole bar is equal to simply NA. Therefore, though there are four variables here, we can write this as y bar equals a plus b plus c plus d. So this shows that there are now pull down network is made up of NMOS transistors. It's only the network of NMOS transistors, and here number of variables are 4. Therefore, this network, pull down network, is made up of 4 NMOS transistors, and there is a plus here connecting each of this variable. Therefore, all these transistors are connected in parallel. So we can write here the 4 NMOS transistors are connected in parallel. That forms the pull down network. So let us say here this is A, B, C, D. There are four transistors here, NMOS transistors. These are all NMOS N-channel enhancement transistors, and all 4 transistors are connected in parallel. As we can see here, there is a common point here, and there is a common point here. One end of this is connected to the ground, the other end is connected to the output Y. Now here, combining the networks which is shown in figure A here, this network which is made up of PMOS transistor, that is the pull-up network, and the NMOS transistor, which is the structure forming the pull-down network. These two networks can be clubbed together. That forms the 4-input CMOS NOR gate. Of course, this is very simple problem. So we have solved 2-input NOR gate, and similar lines we can also write a CMOS structure for 4-input NOR gate. But let us go through a little bit of complex expressions. In example exercise problem 1.6, it is asked here, sketch a transistor level schematic for a compound CMOS logic gate for each of the following functions. 3 functions have been given here, namely the function A is y equals ABC plus D whole bar, and the function B is y equals AB plus C into D whole bar, and lastly we have AB plus C into A plus B whole. The entire thing is complemented. So we need to write a transistor level structure, a schematic, CMOS schematic, for each of this Boolean expression given. First, let us consider the first Boolean expression, y equals A plus ABC plus D whole bar. So now let us develop the pull-up network and pull-down network structures. So the expression is y equals ABC plus D whole bar. Now let us apply De Morgan's theorem for this expression. So applying De Morgan's theorem, the plus becomes dot here, and this entire this ABC becomes a single term now, ABC whole bar dot D bar. So again we can apply De Morgan theorem to bring the variables suitable for the pull-up network. Each variable should be in the complement form. To bring it to that level, we are again applying the Boolean De Morgan theorem for this Boolean expression. So apply again De Morgan's theorem for this expression, gives you first term especially. This term you can apply. This term already the variable is in the complement form. No need to apply De Morgan theorem to this. So applying the first term, so which gives you A bar plus B bar plus C bar. Here it is a dot, so that becomes plus here. Dot D bar is kept as it is, and this shows that there are totally 4 transistors which pull-up network is made up of. Among them, 3 transistors with inputs A, B, and C. 3 PMOS transistors with inputs A, B, C are connected in parallel because of the plus signs, and that structure is in a series with the PMOS transistor with input as D. Okay, so this is the network of the pull-up structure. So here is the network. So we have 3 transistors with inputs as A, B, and C, and those transistors are PMOS transistors are connected in parallel, and that is in series with the another PMOS transistor which is D, and now we connect it to the output Y. So we have here again this forms a pull-up network. Therefore, one end of this is connected to the VDD. So similar lines we can also write pull-down network expression, and rewriting the same Boolean expression. Here in this case, to bring to write the structure, CMOS structure for the pull-down network, we need to have a normal variables, and on the left hand side there should be a complement output function. So now to obtain the complement Y here, so we need to complement on both the sides. So Y becomes Y bar, and the right hand side you can see that already we have a complement here, and again once again complementing that gives you ABC plus D, a double complement that can be written as normal expression here, ABC plus D, and there is a left hand side, it is a Y bar as per the requirement of pull down network. And from this expression we can say that there are uh, the network consists of three NMOS transistors with inputs as A, B, C, and all these three transistors are connected in a series, and there will be one NMOS transistor with input as D, which is in parallel to the above network here, and the network is as shown here. So you can see here, and all three are NMOS transistors which are connected in series, and that with the input as A, B, and C, and this in turn is parallel with another NMOS transistor with input as D. And as usual, we have a pull down network is tied to the ground, and other side of the pull down network is connected to the output Y. Now combining this, the pull up network of figure 1 and pull down network of figure 2, this forms the CMOS structure. The Y here can be clubbed here so that it forms the complete CMOS structure. And let's go through the second Boolean equation. The second Boolean equation is Y equals AB plus C, there is a bracket here, dot D whole bar. Okay, this is also a very simple expression, but this has 4 variables similar to the previous problem. So now let us realize the pull-up network, rewriting the same expression, and let us apply the De Morgan theorem for this. So now we can see here the De Morgan theorem, the dot becomes the plus here. So Y equals AB plus C whole bar plus, instead of dot we have here plus, and D becomes D bar. So now we can see that the second term, this term D, is already in the variable, it is in complement form, but whereas the first term there is a some term here, and so individual variables are not in the complement form. So we need to apply once again De Morgan theorem for this. So let's apply De Morgan theorem for the first term, and let us see what the expression that it results. So now applying for the first term, we get AB whole bar dot C bar plus D bar is kept as it is. And once again we can observe here the first term here, it's not again in the standard pull-up network form. So therefore we need to have individual variables in complement form. So therefore we may have to apply De Morgan theorem to the first term here. Okay, so again applying De Morgan theorem to the first term and retaining the subsequent variables as it is. So we get AB whole bar is equal to A bar plus B bar into C bar as it is plus D bar. So this expression shows that individual variables are in complement form, and left hand side it is again normal output function. So this is actually the standard pull-up network Boolean expression. And now we can rewrite the structure for this. Plus indicates it is a parallel transistors, and dot indicates series transistor here. So here also we have a plus here, and totally there are 4 transistors. Okay, as we can see, number of variables gives you number of transistors. A, B, C, D, 4 variables are there. Therefore, the complete network will have the 4 transistors. AB is going to be parallel, as we can see here. This is a parallel structure, and this is also a parallel structure, and that is in turn in series with the C. We have here C transistor, which is all our PMOS transistor, because pull-up network comprises PMOS transistors, and this complete structure is in parallel with the another PMOS transistor with input as a D. So this complete network forms the pull-up network, and where one end of this is tied to the VDD, and other end is connected to the output function Y. So now let us realize the pull-down structure. Pull-down structure can be realized again with the same approach as we have done for in the previous problem. So Y equals, let us rewrite the same expression, given expression, Y equals AB plus C into D whole bar, and here we need to have output variable in the complement form. So we need to complement on both sides to get output function or output variable Y in the complement form. This becomes Y bar, as you can see here. This is a Y bar which is equal to the same term here, AB plus C into D. Here we have a double complement. It's not visible here, but it is going to be double complement here. And now double complement can be written as single. We can cancel out this double complement and write the expression as it is. So here we have a Y bar which is equal to AB plus C into D. So this is the resulting Boolean equation, and now this is suited for writing the structure of pull down network. So we have here a series connection between AB, and there's a plus here between AB and C. There's a parallel connection, and there is again series connection with reference to this term and the D. So now we can realize the structure here. AB is going to be in series, as we can see here. The network, all this entire pull down network is made up of NMOS transistor. So we have here AB, which is going to be in series. This is a series transistor that is in turn parallel with C here. That is in turn parallel with the C. So this is the variable with the C, and this end is connected to the output Y. This is the output function Y, and now that should complete structure should be in series with the D. So now we have here this complete structure in series with D. So we have here other end is connected to the ground here, and this is a input transistor, NMOS transistor with input as D. So this forms the pull down network, and to get the complete CMOS structure, the pull up network Y can be connected to the pull down network Y, so that complete structure forms the CMOS network. Okay. So that's the problem. And next, let's move to the last one, little complex kind type of problem. This is because here there are various terms here, you can see. So Y equals AB plus C dot A plus B, entire thing is complemented. Now let us write the CMOS structure for this. As usual, let us move on to the realizing this using a pull-up network. We are rewriting the same expression here once again, and now followed by we need to apply De Morgan's theorem for this. So applying De Morgan's theorem to this results in AB whole bar. This plus becomes here a dot, and C dot A plus B whole bar. Okay, now we can see here this again can be we can apply De Morgan theorem to the first term here, that gives you A bar plus B bar, and dot is kept as it is. Here also we can apply De Morgan theorem to the second term, that gives you C bar plus A plus B whole bar. And as we can see here, the individual variables are not in the complement form for in the last term, so therefore it requires one more time we need to apply De Morgan theorem to the last term. So this term can be rewritten as it is, without any change, but here A plus B whole bar now becomes A bar dot B bar. So now we can see here left hand side output function is in normal form, whereas right hand side each variable is in the complement form. That means we can now realize this pull up network using PMOS transistors. Totally we have here 5 transistors. Okay, so let us realize this pull up structure, and then let us come back to the realization of pull down network. So this is going to be the I think there's some change here. Let us see here. Yeah, this is going to be the pull up network. So let us see here, the expression is now, there's some change here what I feel. Okay, so here you can see that A plus B, these two are the transistors which are in parallel, and here we have AB again, which are going to be in series, AB in parallel, and another set structure with AB in series, that is in parallel with the C, and the total structure, these two structures should be in series. Let us see that AB where it is parallel. I think this is the network, as we can see here. Yeah, this is again we are rewriting here. Okay, so let us see that whether no, this is different and this is different. So let us recap here. Yeah, this is going to be the network. I think we have rewritten here once again the same network here, same expression here. So therefore we have here AB, which you can see they are in parallel, two PMOS transistor with A and B, they are in parallel, and we have another structure, as we can see that AB which is in series. AB we have in series connection, and that is parallel with the C, that is again with reference to AB there is a parallel connection which is C. So this forms the pull up network. Similarly we can also write the pull down network. So to make the pull down network here, the same expression here, see, So again, rewriting that expression and complementing on both the sides. Okay, so we have y as y bar here complemented, and double complement can be removed. So we'll have AB plus C dot A plus B. So now we can write the structure for this AB, which is NMOS transistors which are in series. So we have AB which are in series, and another AB which are in parallel. As you can see, AB which are in parallel, and that is in series with the C, and complete network is parallel to the AB. So that is in series with C, and complete structure is parallel to the AB. So this is the pull down realization of okay, the given Boolean expression. This is the Boolean expression which is given. Okay. So with that, let me move to the next one, how to realize a buffer. So this is the exercise 1.7. This is a buffer. Okay, so let me write it here. This is the buffer circuit. Okay, to realize buffer, let us go for pull-up network, y equals a. Okay, and we can't do any changes here. Let us retain this expression as it is. Output function is y, and here we don't have a complement here, but still we can write the input variable in the complement form. Similarly, for the pull down network, output function should be in the y bar. So given expression is y is equal to a, we have to complement on both the sides. So y bar becomes a bar. So though the requirement here is y bar, but right side expression is going to be in the, it should be in the normal form, but here we have complemented variable, so therefore we can write input itself as a bar. So now writing the CMOS structure for this, so we have here pull-up network, which is made up of PMOS transistor. Now here we have a, therefore we can write the input as a bar. Okay. Similarly, the pull-down network, the output function is in inverted form, but here we have an a bar, so we can write here also input as a bar. So now pull-down network is made up of NMOS transistor, so we have here y. To get a bar here from a, we need to have an CMOS inverter here. So we have a CMOS inverter which we already discussed in our earlier videos. So this is the CMOS network. We have an input as a, and output is going to be the a bar here. So we can have a bar here, and that a bar can be plugged up here, plugged in here to get the buffer operation here. So that's related to the buffer. Now let us go to the last expression, which is an XOR gate. So once we know to write the CMOS structure for XOR gate, we can easily write a CMOS structure for XNOR as well. Just an invert the output of this, we get an XNOR. So let us now show how to write CMOS structure for XOR Boolean expression. The Boolean expression for XOR is a b bar plus a bar b, and now we can you can see here the expression already it is in the standard form. As you can see here, a b bar plus a bar b, though here the term may not have individual variables may not have a complement expression here, but at the input you can write complement version. So now we can see here the output function is in the normal form, but right hand side we have few variables in inverted form or complement form, but other variables are in normal form. But wherever variables is in normal, we can write it as a bar in the net structure, and variables wherever the variables are in the b bar or complement form, we can simply write b. So here we have a b bar, so that can be written as using a two transistors. One of them is, instead of a, we can write it here as a bar, and instead of b bar here, we can write simply b. And these two have a dot product here, so therefore these two will be connected in series. Similarly, this a bar b, two transistors can be connected in series, and these two structures will be in parallel to each other. So here we have an a bar, so therefore we can have a here, and we have b here, we can have b bar here. So this complete structure forms the pull-up network with output as y, and here other end of this structure is tied to the VDD. Okay, so this is the pull-up structure for the XOR gate. Now let us realize the pull-down structure for the XOR gate. rewriting the expression for XOR gate, and here the output variable should be in the complement form. So let us complement both the sides. Y becomes Y bar, and here the entire XOR expression is complemented. And now we can apply De Morgan's theorem to this. So this becomes now A B bar whole bar dot plus becomes a dot here, as we can see here. A bar B the whole bar. And now we can apply once again De Morgan theorem to this to bring the complement to individual variables level. So the left hand side is kept as it is. Now after applying De Morgan's theorem, A plus A becomes A bar plus B bar becomes just a B. The dot is kept as it is, and again we can apply separately De Morgan theorem for this and this. This we have already shown. And now for this, if you apply, so which becomes A plus B becomes B bar. So this is the expression for the suitable expression for the pull down network. So now let us realize the CMOS structure. So in the CMOS structure, as we can see here, A bar is there. So this is an pull down structure. Therefore, so we need to have a NMOS transistors. So let us now, A bar is there. Let us connect it A bar here for the NMOS transistor, and these two are parallel. So A bar and B. So A bar here and B will connect it two transistors in parallel, and that should be in series with another transistor A and B bar. So we have another two NMOS transistors, one with input A, other one with input as B bar. So this forms the pull down network. As usual, the one end is tied to the ground and other end is connected to the output Y. When we combine this Y with this network, so it forms a CMOS structure. So with that, we have discussed a couple of problems on CMOS structure, and there are again many problems are there in the exercise of the textbook. So I would suggest to students to go through them, and if there are any queries or any doubts related to this developing CMOS structures, you can write it in the comment section. So with that, we have come to an end of this video. In the next class, we will discuss the other topics related to this VLSI design. Thank you all for watching.